Load-sharing instrumentation for process gas compressors. Precision integration and coordinated control for surge-aware compressor networks. Overview. The instrumentation framework for process gas compressors operating in load-sharing mode is engineered to deliver real-time coordination, precise surge protection, and balanced throughput across multiple machines. Unlike conventional compressor operation where each unit may respond independently to disturbances, the load-sharing model leverages tightly coupled sensing and control loops that synchronize compressor behavior via dynamic performance, surge, and recycle control. All instrumentation and control elements used in this strategy conform to process-specific P&IDs, international safety standards, and integrated automation architectures, ensuring system reliability, responsiveness, and protection under varying process conditions. Scope of supply and integration. Compressor control loop architecture. Each compressor in a parallel network is fitted with a full suite of control instrumentation, including station controller, PIC, governs system-wide flow or pressure. Load-sharing controller, LSIC, maintains balanced surge proximity across compressors. Anti-surge controller, UIC, prevents individual compressor surging through precise recycle control. Integrated control zones, hot recycle, per compressor surge mitigation. Cold recycle, network-wide thermal balancing using shared loops and a centralized heat exchanger. Loop decoupling avoids interaction delays by locally isolating performance, surge, and pressure feedback. Wiring and signal routing, junction boxes at the compressor skid edge interface with all control panels. All sensors, pressure, temperature, flow, vibration, are wired using shielded segregated signal paths, analog 420 milliamps and digital discrete. Diagnostic-enabled HART-compatible devices are used for smart commissioning and fault identification. Hashed instrumentation functionality, primary capacity control. The station pressure controller calculates flow or pressure deviation and issues a shared command, CRSC. Depending on system state, if non-recycling, the load-sharing controller acts on CRSC to increase throughput. If recycling, the anti-surge controller adjusts its output using CRSC to reduce net flow while preventing surge. Load balancing. Each compressor's anti-surge controller calculates its deviation from surge, DV. The load-sharing controller selects the worst-case DV from companion units and aligns its own output. Averages are computed across all compressors to establish a system-wide load balancing set point. Flow rates are then modulated to ensure each compressor runs equidistant from its surge limit. Pressure override control, POC. Dual algorithm control, PI correction for exceeding pressure flow thresholds, predictive control to dampen rapid deviation rates. The POC output always favors surge protection logic and only augments recycle flow when needed. Prevents sharp pressure spikes or suction dips that could destabilize the compressor train. Recycle balancing. When recycling becomes unavoidable, compressors moving away from surge close recycle valves in a staggered fashion. Compressors moving toward surge keep their recycle valves open while others catch up. This ensures uniform valve behavior and extends machinery life by avoiding overuse of any one unit. Cold recycle control. A dedicated cold recycle controller acts before hot recycle valves open. It ensures network-level surge protection without excessive thermal buildup. Its deviation calculation includes predictive derivatives and surge safety offsets to guarantee prompt flow relief. Skid edge interface and layout. Instrumentation junction boxes are explosion-proof, weather-proof, supporting high-integrity environments. Labeled terminals segregate power, analog, and digital loops to reduce crosstalk. Each loop is tested for continuity, calibration range, alarm response, trip logic verification. Special instrumentation considerations. Redundancy for critical measurements. Dual or triple transmitters are installed for header pressure, seal gas flow, lube oil system parameters. Redundant transmitters are integrated into voting logic for fail-safe response. Environmental and diagnostic readiness. All devices exposed to external atmosphere or hot enclosures are rated to IP65 or higher, resistant to H2S, Cl2, or other corrosive gases, calibrated for 40 degrees Celsius to plus 85 degrees Celsius operation. Smart transmitters offer self-diagnostics, remote identification, drift and deviation alerts through the DCS or HMI. Summary. The load-sharing instrumentation architecture for process gas compressors transforms a traditional control scheme into a predictive, synchronized, and surge-aware network. By intelligently distributing load, protecting individual machines from destabilization, and regulating pressure and flow with dynamic precision, this framework ensures maximum operational efficiency with minimum hardware stress. With its holistic integration of hot and cold recycle logic, performance balancing, and override protection, the load-sharing mode supported by this instrumentation layout represents a modern, robust standard for safe and efficient multi-compressor operations. Parallel load-sharing systems. Integrated control strategies for multi-compressor balance and surge resilience. Overview. In multi-compressor process environments, load-sharing systems serve as the control backbone that synchronizes compressor performance to maximize process efficiency, minimize energy consumption, and ensure reliable surge protection. These systems operate by intelligently coordinating the operation of each compressor so that all units remain equidistant from their surge control limits, thereby distributing load safely and responsively across the entire network. The goal is to avoid the inefficiencies and vulnerabilities seen in traditional approaches where one compressor might recycle unnecessarily while others remain underutilized. A properly configured load-sharing framework maintains process stability and protects all machines, even during disturbances, turndowns, or rapid demand swings. Core functional components: station controller, pressure, flow control logic. The station controller acts as the primary regulator of the overall network capacity, either by holding a target discharge pressure or maintaining a desired flow rate at the header. Its output, referred to as the capacity control response, serves as the master command signal for all subordinate controllers in the system. Acts on process variable deviations using advanced PID logic. Generates a unified signal that is distributed to load sharing and anti-surge controllers. Ensures system-wide coherence in response to throughput or pressure demands. Load sharing controllers. Each compressor is equipped with a dedicated load sharing controller that ensures its contribution to network capacity is proportional and surge safe. These controllers dynamically adjust compressor speed, inlet guide vanes, or recycle valve positions based on load conditions and anti-surge margin. Receives the global capacity control signal and modulates local compressor output. Integrates both primary capacity and load balancing responses. Selects the most surge-critical deviation for control comparison. Anti-surge controllers. Designed to protect individual compressors from surge, these controllers calculate real-time distance to the surge line and regulate hot recycle valve positions accordingly. Operate independently, yet communicate with companion controllers. Adjust their output based on local surge proximity and any incoming override signals. Ensure the compressor remains within safe operating boundaries without unnecessary recycling. Functional responses in load sharing mode. Primary capacity response. When net throughput must increase, load sharing controllers raise compressor speed or open flow paths in sync with the station controller's set point. During required reductions in flow, anti-surge controllers take over, adjusting recycle valves to reduce net capacity while maintaining surge protection. This dual-role strategy ensures that no compressor alone bears the burden of flow modulation. Dynamic load balancing. All anti-surge controllers calculate real-time surge proximity DV. Load-sharing controllers use the worst-case DV as a reference and compare it to the network average. The resulting difference is used to bias control outputs so that all compressors remain equidistant from their surge limits. Prevents premature recycling of one unit and ensures mechanical longevity across the train. Pressure override response. When pressure or flow deviates too rapidly or significantly from set point, a proportional integral PI loop counters the deviation. A predictive algorithm identifies excessive rate of change and adjusts recycle control proactively. Whichever signal, surge protection or pressure override is greater is allowed to dominate. Guarantees pressure stability without compromising surge defense. Recycle rate equalization, activated when multiple compressors are simultaneously in recycle. ensures that no single compressor remains disproportionately in a recycle state. When surging is receding, the most open valve is closed faster, while others slow their closure. When surging is imminent, the most critical valve remains open and others accelerate to match its flow. Enhances equipment protection and reduces cyclic wear. Cold recycle loop integration. In systems with a common cold recycle line, a separate control loop modulates the cold recycle valve ahead of individual hot recycle valves. This anticipatory flow adjustment cools the recycle gas through a heat exchanger, avoiding thermal stress across machines. The cold recycle controller receives surge deviation feedback from all units and ensures early intervention before any single unit reaches surge. Summary. Parallel load-sharing systems transform individual compressor control to a networked, intelligent, and adaptive process. Each machine acts in harmony with others, maintaining balanced performance, avoiding premature recycling, and ensuring surge margins are uniformly managed. By distributing capacity control authority across layered controllers while maintaining a unified pressure or flow objective, these systems offer unmatched resilience, stability, and efficiency in high-demand industrial operations. This coordinated approach to load sharing empowers operators to maximize compressor availability, reduce energy penalties from excess recycling, and extend asset life through balanced runtime distribution and proactive surge prevention. Primary capacity control, unified flow or pressure regulation across parallel compressor trains. Overview. Primary capacity control forms the cornerstone of throughput management in parallel compressor operations. It ensures that the total flow or discharge pressure of the compressor network is tightly regulated against process demand while coordinating with both load sharing and anti-surge protection loops. This layered approach not only optimizes compressor output, but also guarantees that surge margins are never compromised, regardless of changing process dynamics. The station controller, responsible for primary capacity control, acts as the central command unit, calculating control responses from the deviation of a key process variable, such as discharge pressure or header flow. Its output signal is distributed across all compressors, enabling seamless cooperation between individual performance and protection controllers. Core functional roles. Station controller functionality continuously measures the selected capacity control variable, flow or pressure, calculates the deviation from set point and applies PID logic to generate a control signal. Issues a station control response, CRSC, to all associated controllers, load sharing controllers for normal throughput modulation, anti-surge controllers for coordinated surge management during recycling. Dual response strategy. The role of primary capacity control varies depending on the operating condition of the compressor network. 1. Normal operation, compressors not recycling. The load sharing controller at each compressor receives CRSC. Each controller multiplies CRSC by a designated load sharing gain. The result is added to the controller's integral response, increasing compressor speed or throughput. Anti-surge controllers remain inactive from a capacity perspective in this mode. 2. Recycling operation, reduced throughput needed. The anti-surge controller at each compressor multiplies CRSC by its load sharing gain. This signal is added to the surge control response to raise the recycle flow rate. Load sharing controllers become passive for capacity modulation in this state. This bifurcation ensures that only the most appropriate actuator, recycle valve, or speed set point is used for flow adjustment, preserving surge margins and reducing mechanical wear. Intelligent flow management, adaptive gain tuning. Each controller applies a specific gain coefficient to the CRSC, allowing proportional influence based on compressor characteristics or operational roles. Prioritized capacity distribution in hybrid trains, e.g., mixed centrifugal and axial compressors. Integral response augmentation. In non-recycling mode, the capacity control signal integrates into the long-term set point tracking logic, prevents overreaction to transients, and ensures stability over prolonged shifts in load demand. Seamless transition between modes. No manual intervention is needed to switch between load sharing and anti-surge dominant states. Control transitions are smooth and continuous, based entirely on the active need for surge protection or throughput boost. Operational benefits. Throughput optimization maintains target production rates without unnecessary recycling or blow-off. Energy efficiency uses performance actuators before resorting to recycle-based throttling, minimizing losses. Surge safety ensures that surge protection mechanisms are always prioritized under restrictive flow conditions. Responsiveness, capable of handling both gradual load changes and sudden disturbances with tailored control actions. Summary. Primary capacity control empowers a compressor network to operate as a unified intelligent system. By distributing a central control response to both performance and protection layers, and letting each compressor determine the most effective local action, this method delivers real-time adaptability, operational stability, and maximum efficiency. Through its strategic role switching and coordinated response logic, primary capacity control enables consistent flow or pressure regulation across complex process environments, serving as the bedrock of safe and effective load-sharing compressor systems. Load balancing equalized surge proximity and performance distribution in parallel compressor operation. Overview. Load balancing is the critical function within a parallel compressor control strategy that ensures all machines operate at an equal margin from surge. Rather than focusing on equal speed or flow, approaches which often fail due to internal performance differences, load balancing uses real-time surge deviation data to equalize risk and workload across the compressor train. By dynamically adjusting each compressor's output based on how close it is to its surge limit, the system prevents premature recycling of any single unit, enhances mechanical reliability, and optimizes process efficiency. Functional logic and architecture. Real-time surge deviation monitoring. Each compressor's anti-surge controller continuously calculates a value representing how close the machine is to its individual surge control line. This deviation, often referred to as dev, becomes the primary input for the load balancing algorithm. Zero dev, compressor is operating precisely on its surge line. Negative dev, compressor is dangerously close to surge. Compressor is operating safely away from surge. Worst case selection for control input. The load sharing controller at each compressor selects the lowest worst case dev reported from its associated anti-surge sections. This selected deviation becomes the control variable used to compare each machine's surge proximity. System-wide average set point generation. The station controller computes an average of all selected deviations from the network of load-sharing controllers. This average serves as the load balancing set point, establishing a reference for ideal surge distance across the compressor train. PD-based load balancing response. Each load-sharing controller calculates the difference between its selected deviation and the station-wide average. A load balancing PID loop then processes this error to generate a correction signal. This signal is combined with the primary capacity control response, if applicable, to determine the final controller output. Control actions and flow redistribution. Compressors operating closer to surge, more negative dVev, are offloaded slightly to increase margin. Compressors with more positive surge margin are tasked with slightly higher throughput. This balancing is done continuously and smoothly, with control outputs biased accordingly. Recycle valves, speed set points, or guide vane positions are adjusted locally. No external operator intervention is required. Loop decoupling support. Balancing logic is supported by isolation between surge, speed, and recycle control loops. Prevents feedback cross-interference and allows each controller to act independently, yet harmoniously. Benefits of dynamic load balancing. Prevents single-point overload. No compressor becomes the sacrificial unit operating on the edge of surge. Avoids unnecessary recycling. Valves do not open preemptively, reducing process inefficiency and wear. Extends equipment life. Thermal and mechanical stress is evenly shared. Stabilizes network dynamics, minimizes sudden pressure drops or flow oscillations that destabilize the train. Summary. Load balancing transforms parallel compressor operation from a group of loosely coupled machines into a coordinated, intelligent network. By dynamically monitoring each compressor's surge risk and redistributing flow accordingly, it ensures equitable operation across the train, maximizing uptime, improving process control, and minimizing unnecessary energy losses. This functionality is essential in complex process environments where identical flow or speed does not equate to identical performance or surge behavior. Through its surge proximity-focused logic, load balancing maintains operational integrity while optimizing throughput and system resilience. Pressure override control, surge-safe stabilization during rapid or excessive pressure deviations. Overview. Pressure override control (POC) serves as a protective augmentation to the standard capacity and surge control strategies in parallel compressor systems. It is specifically designed to address fast or excessive deviations in the network's controlled pressure or flow variable, conditions that can arise during process upsets, abrupt load changes, or system transients. By predicting and correcting dangerous excursions beyond pressure or flow limits, the override control dynamically adjusts recycle flow, but always in harmony with surge protection logic. It steps in only when needed, never compromising the fundamental safety of the compressor train. Activation conditions and control scenarios. Pressure override control is triggered under the following conditions. Discharge pressure control mode. Override is initiated if the pressure rises too high or too quickly. Suction pressure control mode. Override is activated when pressure falls too low or too rapidly. In either mode, the objective is the same: prevent excursions that might cause overloading, trip events, or damage to downstream equipment, while still maintaining surge protection integrity. Dual algorithm response logic. POC employs a two-pronged control logic structure. One-sided PI response, proportional plus integral, monitors the deviation of the pressure or flow variable from a predefined override set point. This set point can be an absolute threshold or an offset from the primary control set point, only activated when deviation exceeds in the defined critical direction. 2. Predictive rate-based response, POP, detects rapid changes in the control variable by comparing the instantaneous value, CV, against a filtered average, CVFG. The predictive deviation DevPop is computed as DevPop equals CV minus CVFG dash SPPop. If DevPop is positive, i.e. pressure is rising, falling faster than allowed, a predictive response term is added. CRPop peak equals KPop's DevPop. This term enhances reaction time, preventing system overshoot or undershoot. Coordination with surge control, the final POC command signal, CRPC, is calculated as CRPOC equals CRPI plus CRPOP. This command is sent to each anti-surge controller, which compares CRP with its own surge protection output. Whichever signal is higher, surge protection or pressure override determines the final action. This ensures POC never undermines surge safety. If the override demand is higher, it adds extra recycle flow to stabilize pressure quickly. Use cases and control flexibility. POC can be configured to respond to any process variable measured by the station controller, not just pressure or flow. This includes suction discharge pressure, intermediate stage pressure, flow rate across critical headers. Set point flexibility and response coefficients can be tuned for aggressive override in highly sensitive systems, gentle correction in slower, stable processes. Benefits of pressure override control. Stabilizes transients, absorbs sharp process shocks without full recycle engagement, prevents overpressure events, avoids sudden shutdowns or safety valve actuations, protects equipment integrity, limits pressure surges that could strain exchangers, piping, or downstream units, enhances process control, supplements primary loops with predictive responsiveness, maintains surge safety, always subordinates to anti-surge logic, avoiding control conflict. Summary: pressure override control adds a critical layer of responsiveness and safety to compressor networks operating in load-sharing mode. By detecting and correcting excessive or rapid deviations in pressure or flow, it cushions the system against transients that might otherwise compromise equipment integrity or process continuity. Through its predictive and proportional integral design, the override control works alongside, never against, surge protection. This ensures that stabilization efforts are always surge compliant, enabling compressors to ride out disturbances with agility, resilience, and control. Recycle balancing, coordinated valve modulation for uniform surge recovery across compressor trains. Overview. Recycle balancing is a targeted control feature designed to manage the behavior of multiple compressors simultaneously in recycle. In parallel compressor configurations, recycling is sometimes unavoidable, particularly during turn-down, startup, or transient conditions. Without intelligent coordination, compressors may recycle unevenly, causing mechanical stress, thermal imbalance, or inefficient load distribution. Recycle balancing solves this by synchronizing the anti-surge valve operations across all compressors, ensuring that no single unit is overburdened and that surge recovery occurs in a controlled, uniform manner. The result is a more stable compressor network with extended equipment life and improved energy efficiency. Functional role in compressor control. When a compressor train enters a condition where recycling cannot be avoided, each anti-surge controller monitors the valve position and rate of change of its counterparts. Based on this shared intelligence, controllers adjust their own outputs to align with the behavior of the group. Two primary operating conditions are handled distinctly. 1. Compressor network, moving away from surge. The unit with the highest recycle valve output, i.e., most open, begins to close its valve faster. The other units slow down their valve closure rates. This prevents premature exit from surge protection in some units, while others still require relief. 2. Compressor network, moving towards surge. The unit with the highest recycle demand maintains its normal surge protection response. The other compressors open their valves more gradually to catch up and avoid lag in response. Ensures no single compressor bears the full load of surge control. Anti-surge controller coordination. Each controller receives periodic data from all other anti-surge controllers in the same compressor train. The controller identifies the maximum recycle valve output currently active. Based on whether the surge condition is improving or worsening, each unit modifies its valve modulation rate, accelerated closure when moving away from surge, synchronized opening when surge risk increases. Flow redistribution. Without process disruption, no change is made to the set points of other control loops, e.g., load sharing or station control. The adjustment occurs solely in the valve response timing, not in the target values. This avoids conflicting signals and preserves the integrity of higher-level control logic. Fail-safe and priority logic. Surge protection remains the primary priority. Recycle balancing actions are always secondary to immediate surge prevention logic. If a compressor is at risk of entering surge, it maintains full valve authority regardless of recycle balance status. Operational benefits. Uniform thermal loading reduces uneven heating across units, which can lead to differential expansion and stress. Reduced valve cycling minimizes unnecessary valve movement, prolonging actuator life. Improved control stability prevents oscillations caused by asynchronous recycle behavior. Process consistency maintains smoother transitions during load reductions or recoveries. Lower energy penalty. Balanced recycling prevents one machine from continuously blowing off, reducing wasted compression energy. Summary. Recycle balancing is a precision enhancement in parallel compressor control architecture that ensures coordinated and efficient surge protection during unavoidable recycling. By aligning anti-surge valve behavior across the compressor network, it protects equipment from uneven stress, enhances system responsiveness, and upholds operational stability. This function underscores the importance of intelligent controller communication in modern compressor trains, delivering not only safety and protection, but also measurable gains in performance, efficiency, and lifecycle reliability. Cold recycle control, network-level surge relief and thermal management in parallel compressor systems. Overview, cold recycle control is an advanced control strategy designed for parallel compressor systems that incorporate a centralized network-level recycle loop, commonly referred to as the cold recycle loop. Unlike individual hot recycle lines attached to each compressor, the cold recycle path offers a shared surge relief mechanism that includes a heat exchanger to cool the recycled gas before it re-enters the suction header. This approach is ideal for handling sustained or long-duration recycling, where using only hot recycle lines could lead to undesirable heat buildup and energy loss. Cold recycle control activates early in the surge risk curve, providing a proactive and energy-efficient method to protect the entire compressor train from surge while minimizing thermal stress. Functional structure and control logic, cold recycle loop components, a dedicated recycle valve connected downstream of the compressor discharge manifold, a shared heat exchanger in the loop to reduce recycled gas temperature, a cold recycle controller typically configured as a specialized anti-surge control element. Trigger conditions and activation, activated when compressors are nearing a sustained surge region, particularly during process turndown, system transients, long-duration capacity throttling, engaged before hot recycle valves, allowing centralized control to stabilize flow network-wide. HASH-CHAR, deviation-based surge risk estimation. The cold recycle controller evaluates a modified surge deviation DV using input from companion anti-surge controllers across the network. DV equals DV min F of V times CRSO plus CRD, where min, the smallest worst-case surge deviation reported by any compressor. Safety on, a fixed bias introduced when surge conditions are imminent. CRD, derivative response based on how fast the system is approaching surge. FB, a flow-based gain factor that adjusts sensitivity based on recycle rate. This equation ensures that the cold recycle control loop begins acting just before any single compressor reaches its own surge limit, providing a protective buffer and buying time for the system to stabilize. Control prioritization and flow relief strategy. First line of defense in sustained surge conditions. Cold recycle valve opens before hot recycle valves. Centralizes surge relief and spreads it evenly across the compressor network. Surge protection hierarchy. Hot recycle controllers retain full authority to act if surge continues or escalates. Cold recycle action complements, not replaces, local surge protection. Thermal management. Recycled gas is cooled before being reintroduced, preventing temperature accumulation at compressor inlets. Improves volumetric efficiency and reduces thermal stress on equipment. Operational advantages. Early surge intervention mitigates surge risks proactively before reaching compressor-specific thresholds. Reduced hot recycle dependency minimizes the need for individual compressors to open their recycle valves, reducing wear and energy loss. Centralized control logic simplifies tuning and coordination compared to managing multiple independent recycle paths. Improved cooling and efficiency utilizes shared heat exchange infrastructure to maintain gas density and operating efficiency. Smooth capacity transitions offers a gentle surge relief mechanism that stabilizes the entire compressor train during prolonged turndown. Cold recycle control provides a strategic, network-wide surge relief mechanism tailored for parallel compressor systems facing sustained low load or dynamic operating conditions. By acting earlier than traditional hot recycle loops and leveraging a cooled gas path, it not only protects equipment from surge, but also improves thermal stability, operational smoothness, and overall energy efficiency. This function is a hallmark of sophisticated compressor control architecture, enabling safe, efficient, and coordinated behavior across complex multi-machine configurations.